All right, good afternoon, everybody. Oh, hang on, sorry. How do I do this? Hello? Oh, there we go. Okay, good afternoon, everybody. So today's lecture, we're talking about a little bit about Linux history, just to set the background for the course, and then we're going to talk about the Linux file system a little bit. If you want to play Pac-Man in your console, you can. So if you've got Linux set up on your system, if you're on a Mac, you can run brew to install Pac-Man. If you're on Windows, or Linux itself, you can run that command there. And you can see, you can actually get the ASCII version of Pac-Man running in your console. I can't actually run it on mine right now because the resolution changes when I switch to projecting. And you need a higher resolution than I get when I project on the screen. But it does in fact work. It's not a great version of Pac-Man, but it's kind of funny that you can actually do this in your console. Okay. So what is Linux? So Linux is an operating system. It's actually more properly called GNU Linux, right? So when most people say Linux, they mean GNU Linux. But the Linux part of Linux is actually what's called the kernel of the operating system. So an operating system kernel, that's the interface between the hardware and the software. Whoop, sorry. Right? All of the other stuff, like a compiler or all the little commands, those are not part of the kernel. Right? And so all that other stuff, well, not all of it, a lot of that other stuff, that came from this organization called GNU. Right? And so you mash the two together, you end up with GNU Linux. Right? Now, Linux was modeled on a kernel from a different operating system called Unix. Right? So Unix was, still is, an operating system. It started as an earlier. It's one of the earlier operating systems in the history of computing. Right. So it came out in the somewhere in the 70s. Unix emerged. Right. Mac OS is based on Unix. Right. So if you're using a Mac, it's fully compliant with a Unix operating system. Linux is mostly compliant with Unix. Windows is not at all compliant with Unix. So Unix was developed at Bell Labs in the 70s. It became successful because it was written in a language that wasn't specific for any particular type of computer. Right? So way back in the early days of computing, you'd buy a computer, and there might be a language that was specific to that particular computer. Right? And you'd have to do programming in that language. So Unix was written in a language called C, which we'll talk about later in the course. Right? And it turns out you can write a C compiler for pretty much any operating system. Right? And so you can, so Unix was written in C, which means you can take Unix and run it on any computing system, as long as you have a compiler for that computing system. Right? Now, when this first came out, it was very expensive. So to buy the operating system itself was probably beyond the ability of most individual users. And so the users for these sort of systems, they're big corporations or universities. Right? Okay, so in 1983, someone by the name of Richard Stallman started this project called GNU. And his goal was to create a Unix-like operating system that was free. Right? So anybody could use it. And so him and his volunteers, I suppose, they got together and they started writing code. Strangely enough, they never actually made the kernel. Right? So they started working on a Unix-like kernel, but they never actually finished. They never finished doing it in the 80s. Right? But they wrote all the other software that you needed to have a usable operating system. Right? So they wrote a compiler. They wrote a bunch of command line tools. So some of the commands that I showed you the other day, they wrote those. So things like ls and other commands, right? They actually created programs for those commands. Okay, so this being a free project, right? So the goal of this project being to create free software, right? No one was paying for this. So progress was not particularly fast, right? Roughly 10 years later, a graduate student in Finland by the name of Linus Torvalds decided, hey, I've got this computer, right? It's running on this 8386 processor. So if that number doesn't mean anything to you, that is the Intel processor that is, well, many generations now, the predecessor to the CPU that's running in a lot of your computers. Right, so this is an old Intel processor. He had one of these. He decided, hey, I want an operating system for this processor, and I want it to be based on Unix. Right? And I can't afford to buy one, so I'm going to make my own. Right? So he started writing the kernel for a Unix-like operating system. He didn't have the tools. He didn't have a compiler. He didn't have any of the command line tools or anything like that. But GNU had those. So they got together, and GNU Linux was born. Right? So the kernel comes from Linux. Right? The other supporting tools, they come from GNU. Right? So where is Linux used today? So it's used in a lot of places, but most people never see it. Right? So it's dominant in most networking infrastructure. Right? So all the stuff that runs the internet, not all of it, a lot of the stuff that runs the internet runs on Linux. Right? I think pretty much every supercomputing cluster out there runs on Linux. Right? If you have an Android smartphone, it's running Linux. Right? And Android runs 70% of the smartphones in the world. Right? Embedded systems I mentioned the other day. So these little devices, little devices with computers inside of them, many of them run Linux. Right? Many of your modems or your internet routers are running some version of Linux. It's uncommon on the desktop. Right? So I think the usage rate on desktops is somewhere around 2 to 5%, right, of computers on the desktop are running Linux, right? Unless you include this thing called Chrome OS. So Chrome OS is a Google project that runs on typically inexpensive notebooks, typically for education. So kids, right? Typically for computers for kids. Turns out there's a lot of these computers. They run Linux. Okay, now you might see this term POSIX kicking around, right? Which sort of looks like Unix, sort of looks like Linux. It's not really the same thing. POSIX is a set of standards, so it's created by a standards body that describes standards for maintaining compatibility between operating systems, right? So I guess there's 3 dominant operating systems now. There's Mac, there's Linux, there's Windows, right? It would be nice if these computing systems could interoperate. Right? POSIX is the set of standards that tries to describe an operating system in a way that's abstract enough that you can sort of, that the different operating systems can work, can be compatible with one another. Right? Okay, so if you see something that's POSIX compliant, basically you're talking about Unix, right? Or Mac. So Mac, turns out, is POSIX compliant. Right? Linux is mostly POSIX compliant. Windows is not POSIX compliant. Right? So if you ever see this term POSIX, it's just describing a set of standards. Okay, now what about Bash? So Bash it's just software. Right? So Bash is what's called a shell. And it's software that runs in what's called a terminal. Right? And the reason these things are called terminals is because they used to look like this. Right? So that used to be, this used to be the way that you would interact with a computer, right? So there's a keyboard there, right? So you can type into the keyboard, you can type into the terminal, right? Press enter or something, right? The computer would interpret your command. If it generated output, that thing right there, that's a printer. So it would print the output, and that's what you would see, right? So there was no video, there was no screen or anything like that, right? And of course, before this, it was even more primitive, right? A little bit later on, once we had the ability to actually make something that was basically a television, right? An old television, right? Have any of you actually seen an old cathode ray television? One of these big boxes, probably about yay thick. Big piece of glass inside it. Yeah, it's a giant piece of glass. A lot of you, I don't think have seen them. I think most of you have only seen these flat screen televisions. So a television used to be this huge piece of glass. Like you'd pick up a television like weigh like hundreds of pounds, right? That's one of these, right? And so the technology there is very different than the technology that's used today, right? But now you've got an electronic screen that can convey information to you, right? And you'd have a keyboard, and now everything's in one nice box, right? So today, these terminals, they still live on, right? So whenever I show you one of these, right, that's a software terminal, right? And this is basically, this resembles something like you would see back, I guess, in the, I don't know, the late 70s, early 80s, somewhere in that time period, right? And this is what the interface to your computer would look like, right? There's no windowing system, right? There's no pretty graphics or anything like that, right? You just get something that looks like this. Okay, so your terminal, that's the thing that lets you type, and then it can so you can type commands into it, and it can display the output of commands, right? But the thing that actually interprets the commands, that's called a shell, right? So your shell is the software program that interprets text to determine meaning, right? In other words, when you type something in and press enter, it's the shell that interprets what was typed in and tries to do something with it, right? Of course, where does the text come from? Well, it comes from a terminal, right? And it turns out there's a whole bunch of different shells. Right? So somewhere I've got that open, I hope. Right, so if you click on that link there, it'll take you to this page here, right, on Wikipedia. And if you scroll down a bit, you'll see that, right, starting in this table here, it lists a whole bunch of shells, right? So there's the Thompson shell, there's the Bourne shell, right? And notice the dates here, right? So 1971, 1977, keep on going, and it keeps on going, and it keeps on going. Right, there's lots of shells that are or were in use on today's computing systems now. Right? If we scroll back a little bit here, there's the Z shell. Right? If you have a Mac, that's your default shell nowadays. Right? So starting, I can't remember when. A few years ago, they switched to the Z shell. Right? On Linux, it's currently Bash on most Linux distributions, not all, but most. Right? Run a shell called Bash. It's called Bash because it's based on the shell called Bourne. Right? So Bash is the born again shell. Right? It is the default login shell for many Linux distributions. Right? And Mac used to use it. I guess they switched in 2019, which is annoying for this course because now I have to deal with people using Macs and they're actually using the Z shell when they should be using Bash. Right? So in this course, everything that we do, well, everything for the first few weeks, we're assuming you're using Bash. Right? If you're on a Mac, you have to be a little bit careful because the Z shell is not exactly the same as Bash. Right? The commands don't all behave the same, and it's not always clear how they differ. Right? So you have to be a little bit careful, read the assignments carefully when you're using if you're using a Mac. Because there will be different instructions for some commands when you use a Mac. Yeah? Would
you recommend you just, if you have a Mac, just make Bash your default shell?
No, yeah, you don't have to do that. You can just switch to Bash when you need to do a 220 assignment, and then otherwise use the Z shell. Right? Mac has made it so that the Z shell is tied in quite tightly with the operating system. So if you're a Mac user, learn to use the Z shell. Right? Of course, for this course, you have to use Bash. Right? So just switch to a Bash when you're when you're doing the assignments. Right. Okay. So central to the Linux operating system is something called a file system, and it's central to most operating systems that you would interact with. Right? And so the Linux file system is based on the Unix file system. So I'm going to take you to this link right here, because it's sort of important to understand how the Unix file, well, to see what the philosophy of the Unix file system was when it was designed, right? And the fact that it still lives on today, right? And Linux has to deal with the fact that the Unix file system was designed a certain way. Okay, so notice problems in the design of Unix. So this is written by one of the people who actually designed the Unix operating system. So let's scroll around to here. So in Unix, a file is just a big bag of bytes, right? So what he's trying to say here is that in Unix, right, if you have a file, right, the file is literally just raw information, right? So it's just a bunch of ones and zeros, and that's it. That's your file, right? There's no way, right, In particular, there's no capability to store information about the file type, or there's no way to store a pointer or a reference, right, to some other information regarding the file, right? So in other words, in Unix, there's no way to store information with the file that says you should use this application to open it, right? You know, in Windows, if you click on a docx file, you get Word pops up, right, and something happens, right? On Mac, if you click on a PDF file, Adobe or something else pops up, right? Or whatever, right? So in more modern operating systems, there is a way to store information that's not just data that the file has, right? There's a way to store information about the information, right? So there's metadata. Unix doesn't have that capability, at least not natively, right? Okay, now, so if everything's just raw data, right, what else does Unix assume, right? So it assumes everything's just a byte stream, right? So a byte stream, again, is just a sequence of zeros and ones, right? That's all it is, right? So that, all your files, right, as far as Unix is concerned, it's just a sequence of zeros and ones, right? But it goes beyond that, right? On Unix, you'll often see something like, on Unix, everything is a file. That's not exactly true. What they really mean is that on Unix, Unix thinks that a lot of things, it's just a sequence of zeros and ones, right? It's just a stream of bytes. And that includes hardware devices, right? So in other words, Unix thinks that your disk drive or your flash drive or your USB drive, right, it's just supplying a sequence of bytes, right? A sequence of ones and zeros. And this is great, right? Or it was great back in the 1970s, right? Through the 80s and maybe a little bit longer. Right? So notice it says this metaphor was a tremendous success in Unix, right? And a real advance over a world in which, for example, compiled programs could not produce output that could be fed back to the compiler, right? And then a whole bunch of tools sprang from this abstraction, right? So if everything's just a stream of bytes, what can I do with the stream of bytes, right? And we'll show you in the course what you can do with the stream of bytes, right? Now, so this is a bit of a problem because this is all baked into the Unix operating system, right? Everything is just a stream of bytes, right? Which was useful back in the day, right? But now it's causing problems, right? So in a modern operating system, right, when you click on a file or something, you expect something to happen with the file, right? In other words, you don't want to treat the file as though it was just a bunch of bytes, right? You want to associate other information with the file, right? And so that's a problem, right? So when I click on an icon in your window-based operating system, right? So you double-click on whatever, File Explorer, or you double-click on Mac on, I can't remember what the Mac stuff's called. I don't use it enough, right? But you double-click on some icon on Mac, and then something magically happens, right? That doesn't fit into this whole everything is just a stream of bytes analogy, right? And so now, if you're working in a Unix-like operating system, or if you're developing something that is Unix-like, right, you have to work your way around these problems, right? Mac in particular, the Mac operating system, even though it's built on top of Unix, there's all sorts of crazy things you can do with files on Mac that you can't even do on Windows either, right? And so this is a problem that this is a limitation that you have to realize exists when you're working in an operating system like Linux. Right? Okay, so the file system is just the part of the operating system that controls how information is stored and retrieved. Right? So, for example, right, your computer probably has a disk drive or a flash drive or something in it, right? That stores your data. Right? So your file system controls how data is stored and retrieved using whatever hardware devices are on your computer, right? And each operating system has its own implementation of a file system, right? So Windows, most of your Windows, I guess a modern Windows machine is something called exFAT, right? It might be FAT. I guess it's possible that you have an NTFS formatted file system, right? So Windows has its own particular file systems, right? Mac has the Apple file system, so AFS. Right? Linux has dozens of different file systems, right? So there's the EXT family of file systems, something called Riser, something called XFS, and so on and so on and so on and so on, right? Anybody can invent a file system, and it turns out people do make them and make them available, and then people use them, right? So there's lots of different file systems in Linux. All right, so a device is basically a piece of hardware that can store files, right? So something like a disk drive or a flash drive, CD-ROM or DVD-ROM if you've ever seen one of those, right? So these are all examples of a hardware that you can use to store files, right? So that's what we call that a device, right? Now, how does Unix or Linux treat devices? Right? So this is interesting, right? So it's a piece of hardware that lives in your computer. How do you access that piece of hardware, right? So in Unix, Unix just says, look, for every device that's on your computer, we're going to associate a file with that device, right? Now remember, what's a file? A file is just a sequence of zeros and ones, right? So if I associate a file with a device, if I write to the file, right, that's like writing a sequence of zeros and ones to the device, right? If I want to read from the file, that's like reading a sequence of zeros and ones from the device, right? And so reading and writing to a device lives behind this abstraction, right, where you're just writing a stream of zeros and ones or writing a stream of zeros and ones to a file, right? And this abstraction is wonderful for the people who are using the operating system, right? Because whoever is using the operating system, you don't need to know that you are writing a file to a disk drive or a floppy disk or CD-ROM or magnetic tape or whatever else, or to the network, right? You just pretend you're writing stuff to a file and everything just magically happens, right? The operating system takes care of all of the details of actually writing to the device, right? And so that's kind of cool, right? I don't care where the data is going, right? I just write it to a file and then it magically goes to where it needs to go. All right, so how do you represent a file, right? So if I want to save a file somewhere on your disk drive, right? So how does the operating system actually do that, right? Now, if the contents of a file is just zeros and ones, right? I can imagine, or you can imagine, right? That your disk drive is just a giant array, right? This is not at all true, right? This is so far from the truth that it's not even funny, right? But we can just imagine it's just a big array, right? Because I've got this abstraction that files are just zeros and ones, right? Just streams of zeros and ones. So this big gray empty box, that's just an empty array, right? So there's my empty disk drive. If I save or write a bunch of files to the disk, right, I can imagine that each file, the information for each file, just lives in part of the array, right? So the first, I don't know how many elements of my array, right? That's the file that's in red, right? And then the next sequence of elements in the array, that's the file colored in green, right? And there's another file, and there's the contents of another file, and there's the contents of another file, right? So you can imagine that this is the way that your operating system is storing information on the disk. It's not at all true, right? But this is good enough, right? Somewhere there's space for the file, for the information that lives in the file, right? Okay, so let's imagine that this is the way it actually works, right? The operating system needs to store information about these files, right, in order to retrieve the information that's in the file, right? So if I want to get information on the red file, what do I need to know, right? Well, I need to know that the red file starts at index 0, right? And I need to know that it ends here, right? If I want to get information about the green file, what does the operating system need to know? Well, it needs to know the green file starts there. Oh, wait, can you see my mouse? No, you can't see my mouse, right? You need to know it starts there, and it ends there, right? And so on and so on and so forth, right? And to be really useful, you might want other information associated with the file as well, right? So for example, is there any way to make this bigger? Shift? No, there isn't. Okay, so if I pop open Windows Explorer in my Ubuntu, running inside Ubuntu, right? So these are the files that you see in your directory that contains the notebook files, right? Notice what Windows tells you, right? It tells you what date was the file last modified on, right? That's useful information, right? How big is the file? Also useful information, right? And you can imagine there's lots of other useful information that you might want to know, right? So what other information might be useful? Well, stuff like when was the file created, right? When was it last modified? So when was the last time you wrote to the file? When was the last time you read from the file, right? And all sorts of other stuff, right? This list can go on and on and on and on, right? And so, how does Linux organize all this information? Right? And so your operating system has a data structure called an inode, right? So an inode is just a data structure that the operating system maintains, right? An inode stores information about the contents of a file, right? So, what device is the file stored on, right? What type of file that file corresponds to, who owns the file, how big is the file, and a bunch of other stuff, right? What's not stored in the inode, right? So what's not stored in the inode? The data that's living on the disk is not stored on the inode. So the inode does not store the contents of the file, right? It stores information about the file. Okay? And so for every file, there's at least one inode, right? Makes sense, right? So your operating system has to keep a collection of inodes, right? With every inode is assigned a unique integer number, right? So that just identifies the inode, right? So every inode has an integer value, right? And that's the identifier for the inode. On a given device, right, so on, say, my disk drive, the inodes are unique, right? If I have 2 disk drives on my computer, though, you can reuse the same inode number on both devices, right? So inodes are unique per device, but they're not unique across devices. Okay, so that's what an inode is, right? So an inode stores information about the contents of the file. Right? What's not in the inode list here? Right? So one of the things that's not in that list is the name of the file, right? Which seems very weird, right? If I'm storing information about a file, right, where is its file name? Right? It's not in the inode. Right? So in Linux or Unix, right, there are these things called directories. A directory is just a folder for most of you. Right, so back here, this is the contents of my CISC220 notes bash folder, right? The folder scripts, right? That's another folder. It's got some folders in it, right? And each one of those folders, there might be some other files, right? So a folder a directory in bash or Linux is what you know as a folder. Right? So a directory, turns out, is just another type of file. Okay? The contents of the file is basically a table that stores a file name and the inode number that contains the rest of the information about the file. Right? So your directory looks like this table here. Right? So the contents of my directory, remember, a directory is just a file. Right? The contents of the file, there's some number here, that's the inode number. Right? And the file name, right, that maps to that inode number, right? So the directory images, right, maps to the inode number 662400, right? The directory scripts maps to the inode number 655381, right? And the file name animals.txt maps to the inode number 662411, right? So your directory, that's where the file name lives, right? The file name is not explicitly bound to the file itself. Right? And so what I can do is I can actually change that file name. Right? So I can come into this directory, change that name, right? So I can rename it to something else. Right? So say big A animals.txt, right? And after I rename it, it still points to the same inode number. Right? So it's still the same file, it just has a different name now. Right? So file names are kept separately from the contents of the file themselves. Right? The file names are stored in the directories. Any questions about so far? All right. Okay, so there's something called hard links. There's also something called soft links in Unix. So a hard link is a directory entry that maps a file name to a file. Okay? So every file has at least one hard link. So a hard link is a directory entry that maps a file name to a file. Right? So in other words, each row you can imagine is a hard link. Right? Each row of the directory you can imagine as being a hard link. Right? Every file has to have at least one hard link. Right? Which makes sense, right? I need to somehow map the name of the file to the contents of the file itself. Right? So I need a hard link to do that. Right? And so that table on the previous slide, that's basically showing you the hard links for the files in some directory. Right? Okay, now it's possible to create additional hard links to a single file. Right? So I can make a hard link I can make a second hard link or a third hard link to the same file. Right? And so what I mean by that is, right, I can create another file name. Right? So instead of animals.txt, I can create another entry in this table, right? And maybe call it big A animals.txt, right? And I can make that file name point to that same inode, right? So I can now have two file names that map to the same file, right? Or map to the same inode, right? If I use either animals.txt or big A animals.txt to edit the file, right, then the contents of the file change, and both file names appear to correspond to a file where the contents have changed. Right? So it's like if you had two references in Java that both refer to the same object. Right? Question?
Are you able to have the same file name, or two or more copies of the same file name in the same directory?
Can you have two file names in the same directory? Two identical file names in the same directory? The answer is no. Yeah. Okay, so a little bit later on, I think I'm going to show you how to make hard and soft links, and I'll show you what the difference is between the two. Right. Okay, so I'm now going to jump to the notebook, and we're going to use the notebook and the terminal to play around in the Unix file system. Okay, so the notebook that we're interested in is the file system notebook. I'm just going to make the text bigger so you can actually read it. Okay, so everything that I talked about is actually at the top of this notebook, right? Including up to the hard links here, right? Okay, so in Linux, Linux has something called a file system hierarchy standard, right? So in other words, there is a standard which there's a standard organization of the directories of the main directories in a Linux system, right? It's called a standard, but it's optional, so it's not really a standard, right? Most Linux distributions follow this standard. Not all follow this standard, right? So all it does is define the directory structure that you can expect to see in a Linux distribution, right? Now Mac OS, the organization is similar, but it's not exactly the same. Right? So everything I'm talking, if you look at your Mac OS operating system, when you try to apply this stuff to your operating system, it's not going to look exactly the same. It's close-ish, right? Close-ish. Okay. So what you need to know is that the way that the Linux file system works is there is a directory that contains all other directories on your file system, right? So there's a top level or uppermost directory. It's called /, right? Or root, right? Most people call it root, right? But the symbol, its name, is the /, right? So that's your root directory. Inside that root directory are all of the other directories for your file system, right? Linux is a bit unusual in that there's only one file system, right? So there's one root directory, and it contains all of the file systems. That contains all the contents of your entire file system. Windows doesn't work like that, right? So if you're on a Windows computer, you know that there's a C drive, there's a D drive, there's an E drive, there's an F drive, right? Those are all the root names for separate file systems. Right? So Windows doesn't work this way. I think Mac does work this way. So Mac does have a root directory. Okay, so if I want to go to the top of this root directory, right? I want to go to this directory root and see what's in it. Right? How do I do that if I'm on Linux? Right? So I open up a terminal, right? And I can use this command called cd. Right? So cd is what's called a built-in command. Right? So it's a built-in shell command. cd is short for change directory. Right? So it changes what's called the current working directory of the shell, right? And it switches to whatever directory you specify. So if I type cd/, right, that's going to switch to the root directory. So I'm going to do that into the terminal rather than in the notebook. If you have the notebook open, just do it in the notebook though. Right? So right now, in my shell, right, that tells you the current directory that you're in. Right? So it says something like /2023 winter /sys220/notes/bash. Right? So that's the directory that I'm currently in. If I type cd root, right, so / and press enter, right, notice that changes to the root directory. Right? So now, when I type something into the shell, right, the shell thinks that it's in, well, the shell is in the root directory. Right? Okay, so that's what the cd command does, right? It changes the current directory to the specified directory. Right? There's another command that's useful. Well, it's less useful today on most shells today, because most shells today are set up so that it tells you what your current directory is. Right? So for example, my Ubuntu shell, my bash shell in Ubuntu, right, it tells you what the current working directory is there. If you look in the title bar, it's also up in the title bar. Right? But that's not necessarily the way that your shell is configured. Right? If you want to know what is the current working directory, the command pwd will tell you what is the current working directory. Right? So pwd is short for print working directory. Right? And when you run that, it prints the name of the working directory. Right? So it prints / or root. Right? If you want to know what's inside of a directory, right, you can run the command ls. Right? That's L, not 1. Right? So ls. Ls is short for list. Right? So it lists the contents of the directory. Right? You can run it in the shell, in the terminal here, or you can run, in the Jupyter Notebook, or run it right in the terminal. So I type in ls, and it prints out a bunch of stuff. Right? So it's printing the contents of my root directory. Right? Depending on how your shell is set up, it may or may not be color-coded. Right? By default, I think on Mac and Linux, if you use Ubuntu anyway, the color coding is turned on. That may not be the case, though, depending on how you configure your shell. Right? So here you can see anything in blue. Right? Anything in blue, that's a directory name. Right? So there's a directory called boot, there's a directory called dev, there's a directory called etc, and so on and so forth. Anything in this greenish color, these are what are called links. It's not important what those are right now. Right? For our purposes, though, they are in fact, I can show you this. Right? So there's something called bin. Right? Bin is what's called the link. It points to a directory called user bin. Right? So anything in blue, that's an actual directory. Here, anything in green with an arrow beside it is pointing to another directory. So in other words, it behaves as though it were a directory. I don't have any regular files here, so we'll see examples of those shortly. Yeah, I don't have any of those. Right. So ls lists the contents of a directory. Right. So you just saw 3 commands. Right. Now, if you want to know how to use a command, is there a built-in way to do so? Right? And the answer is there is. It's kind of clunky, and there's more than one way to get information about a command. So it's extra clunky. Right? One way to do it, of course, is to just open up a web browser and search, right? Which might be the easiest way for most of you. If all you have is a terminal, though, then one of the ways you can do it is you can ask the terminal for help, or you can ask the shell for help. Right? So up here I tell you that cd is called a built-in command. Right? So there are these things called built-in commands. Right? pwd, also a built-in command. right? And then there's ls, which is just a command, right? So not a built-in command, right? So a built-in command is a command that comes as part of your shell, right? So it's something that your shell can natively do, right? So in other words, it's built into the bash shell, right? cd, pwd, these are native commands. ls is not a native command, right? What that means in practice is that ls is some program that the shell has to run in order to execute the command, right? So not a built-in. To get information about different types of commands, you have to use different commands, right? I told you it's clunky, right? So it's a bit clunky. All right, so if you want help on a built-in command, you can type man built-ins. So let me just show you what that does if you actually type that in. Sorry. Man built-ins. Right? And so that gives you what's called a man page. So man is short for manual, right? Man is a program that the shell knows how to run that displays the contents of a help file in a particular way, right? So this lists all of the built-in commands up here, right? If you want to figure out how to use one of them, you have to scroll through this man page to figure out how to get the information for it. So let's not do that right now. I'll show you how to read a man page, I think, in the next lecture. Right? If you happen to remember that a command is a built-in, you can use help. Right? So for example, I can type in help cd. Right? And this works because cd is a built-in command. Right? And so when you type that in, you actually get the information page for the help command. Right? So this is the default documentation that you get when you ask the shell for information about one of its built-in commands. Right? And you can see that up here, it says that the cd command has the following form. Right? I'll explain how to read this later on. Right? I'm just showing you right now how you can access the actual help pages for these. Right? And then it's got some information here that you can read to figure out exactly how the cd command works and what the different options do. Right? Similarly, you can type in help pwd and you can get information about help. About pwd, the print working directory command. Right? If a command is not built in, you have to use man. Well, you don't have to use man. One way to get information is to use the man command. Right? So type in man ls, and you're going to see a giant page of information. So there's man ls. Right? So there's the first page. I'm just going to press the space bar a bunch of times. Right? It goes on for quite a while. Right? So there's a lot of information about this one command ls that does nothing but list the contents of a directory. Right? Okay, so we're in the root directory, right? I know how to change to the root directory using cd, right? I know how to print the name of the directory by using pwd. I know how to list the contents of the directory, right? So if you're in the root directory, then the Linux file hierarchy standard says there has to be certain directories, well, there should be certain directories in the root directory. There should be a directory called bin. So this is my picture, right, using a file manager-like representation. Right? There should be a directory called bin. There should be a directory called home. There should be a separate directory called root. Right? This directory root is different than the root directory here. Right? There should be a directory called user, and so on and so on. Right? So the standard says that these directories should be the ones that exist. Don't memorize this, right? This is just information so that you know that this standard exists. Right? Okay. That directory home, right? Inside that directory home, there will be a directory that corresponds to your user account, right? So on my computer, right? If I go to home, right? So I'm going to use cd, right? I'm going to switch to the home directory, right? I'm going to list the contents. You can see that there's a directory that belongs to me, right? So it corresponds to my username on this computer, right? Homer Simpson, he's got a directory too, because I made one for him on this computer, right? If there's many users on your system, they'll each have a directory in the home directory, right? So the home directory is where user files live. Right? What time is it? 11:16. Okay. All right. So using this command ls, So I just use cd to change to a directory, right? I can use ls to list information about a specified directory. Right? So back to my shell. Here. Right, so let's go back to the root directory. So cd root. Right? If I just type ls, right, it lists information. It lists the contents of the current directory. What if I wanted to list what's inside the home directory? Right? So I can type in ls, and then I can type /home. Right? So root home. Right? Press enter. And it prints out the two directories, Burton and Homer Simpson. Right? So when I specify the name of a directory, starting with /, right? So starting with the root directory, right? This is called an absolute path, right? So /home, right? That is the absolute path name of the directory called home, right? Absolute path. Now look, I'm in the root directory right now. Right? So I'm currently in root. Right? I know that inside the root directory there is a directory called home. Right? So I can also type in ls home. Right? In other words, I don't have to put the /, right? And it still works. Right? So when you don't put all of the directories starting from / in front of the name, you're using what's called a relative path, right? So home is the name of the directory relative to the current directory, right? Which happens to be root, right? So I can do ls home /Burton, right? So this is a relative path, right? So this is the relative path to my home directory, right? Starting from the root directory. Right? So I can list all the files that are there. Right? If I want the absolute path, I have to start at root. Right? So /home /Burton, that's the absolute path of my home directory. Right? And it does the same thing. Okay, so let me go to the home directory. So I'm going to switch to home. Okay, so now I'm in the home directory. I can list the contents of my directory, because I know there's a directory called Burton inside the home directory. Right? And that works too. Right? So again, I'm using a relative path. Right? So the directory named Burton, that's the directory relative to the home directory. Right? If I want to use an absolute path now, I have to type in ls, right? Start at root, so start at the top of the hierarchy, and type in all the directory names until I get to the directory that I want. Right? So /home /Burton, that's the absolute path name of my directory. Right? So there's a distinction between absolute paths and relative paths. Right? Absolute path starts at /. Relative path starts at the current directory. Right? And that's enough for today. We'll continue this, I don't know when, sometime later in the week. Any questions? All right.